Hello, welcome to Thermodynamics 101, Energy Balances of Closed Systems. This video will specifically address the stirred fluid problem. So the stirred fluid problem, something like this. You are given a tank. You are given a rigid and well-insulated tank. I know that's a really horrible tank, but I'm not an artist, I'm an engineer. And there's a paddle wheel within this tank. And the paddle wheel's spinning, it's stirring whatever fluid is in this tank. It could be a gas, it could be a liquid, it doesn't really matter. And the question is, what does the energy balance look like over this tank? How can we solve for the power given the internal energy change? How can we solve for the internal energy change given the power? Let's talk through it. Let me move my tank off to the side. I've got a little more room to write. Step one of any thermodynamics problem is to draw the picture of the system. That is done. Step two is going to be draw a boundary around the system that we want to study. I think the tank is the system I want to study. I'll draw a little boundary here and label all of the energy flows going into and coming out of that system. So in this case, I have work going into the shaft of the paddle wheel. I write it as W because it is work, because it is something physically moving, as opposed to Q, which we use for heat transfers. So W in. I can write that as an energy. I could also add a little dot to the top, which makes it an energy rate or a power. For the sake of this example, I think I'm going to keep these as all just straight energy flows. There could be heat transfer between the tank and the environment, which I'll write as Q for heat transfer, E and V for environment or envelope, your choice. Most of the time, the way this problem is written, you can ignore. They'll tell you it's a well-insulated tank, and you can say heat transfer between the tank and the environment is 0. But be careful, that's not always an assumption that you can make. We're going to make the assumption for the sake of writing this energy balance because it makes our life a little bit easier. There are no other energy flows that I can think of going into or out of this tank. There are no ports, there are no nozzles. I think this step is done. So step 3 is to actually write out the energy balance. And the generic form of the energy balance equation is exactly the same for every problem, every time, everywhere, any place. Energy in minus energy out plus energy generated equals the change in energy stored in the system, which can also be written as the energy at the final state minus the energy at the initial state. And commonly we write the final state as state 2 and the initial state as state 1. In this particular case, for energy in, I have work going into the system. That's the only arrow crossing into the system. So energy in is work in. Energy out, easy, simple, 0. Nothing is leaving the tank. Energy generated is pretty much reserved for chemical reactions and things like living creatures that emit heat energy. There's nothing living in the tank. There are no explosions or anything going on in there, so we can write energy generated as 0. That takes care of the left-hand side. On the right-hand side, let's expand energy 2 and energy 1 a little bit. So energy 2 is going to be equal to the mass of energy in the tank. Sorry, the mass of energy, just the mass of the tank, mass of fluid in the tank, times the 3 macro components of energy associated with mass. A mass can have potential energy, which is the mass times the acceleration due to gravity times the height of the fluid. We're actually writing state 2. Let me clean that up a little bit. Mass can have kinetic energy, which is the mass times the velocity at the state squared divided by 2. And a mass can have internal energy, which we represent with U. Energy at state 1. Same idea, different subscripts. So the mass again times the potential energy at state 1. Kinetic energy at state 1. And the internal energy at state 1. 9 times out of 10, 99 times out of 100, I don't know, more often than not, I would say, we can neglect changes in potential energy and changes in kinetic energy. And in this particular case, the tank is not going anywhere, it's not doing anything, it's just kind of sitting there. It's pretty safe to assume kinetic and potential energy changes are negligible. So from this whole big long equation that we started with, it all reduces down to, on the left-hand side, work in, and on the right-hand side, mass times the energy at state 2 minus the energy at state 1. Or we could also write that as the work in per unit mass of fluid equals the change in internal energy. So let's look at a specific example. Let's say that the tank is 0.2 cubic meters, and we're given, so let's write that, say that that's my volume. And I'm given a density, I don't know why I have my labels on the right-hand side here. I'm just going to go with it for now. I've got a density of 1.2 kilograms per cubic meter. And let's say I'm given the power into the tank, into the shaft. So the work of the shaft is something like 4 watts. I'm going to need a little more space. I'm running out of room. And it runs for 20 minutes. And the question is, what is the internal change, the change in internal energy of the fluid in the tank? We can actually solve that. Let's look here. On the top, work in. We're going to take our 4 watts times 20 minutes. A watt is a joule per second. And don't forget to convert units. So 60 seconds per minute. There we go. And on the bottom of the equation, we have, let me keep, on my never-ending paper here, I can just keep scrolling to add more space. Take my 0.2 cubic meters times 1.2 kilograms per cubic meter. On the top, 4 times 20 times 60, I've got 4,800. Sorry, I'm talking slow, I'm writing slow. Minutes cancels out, seconds cancels out. I've got joules on the top, on the bottom, meters cancels out. Got 0.24 kilograms. That becomes 48 divided by 24, that's 20,000 joules, or 20 kilojoules. Ta-da! Thanks for watching.